local search algorithm and optimization problem. This is also comes under heuristic search algorithm, but here we are reducing the space complexity. We try to reduce the space complexity. So whatever space complexity we have in the previous examples, we are trying to reduce the space complexity here in local search algorithm and optimization problems. Now let's talk about this type of algorithm. If the path to the goal does not matter, means अगर हम लोगों को पाथ से कोई मतलब नहीं है, in the local search algorithm and optimization problem, we are trying to reduce the space complexity. So when we try to reduce the space complexity, when we doesn't have to store the nodes, let's say if I am not exploring that node, so I'll just remove that node from my memory. So where it will be applicable, it will be applicable to those search where path is not required. So it is saying that if path to the goal does not matter, we might consider a different class of algorithm, ones that do not worry about paths at all. So if we doesn't have to worry about the path, we'll choose local search type of algorithm. This local search algorithm operate using a single current node. So all the time we have only one node in the memory. That node is called current node. Okay, rather than multiple paths. So instead, in the previous example, we have seen that in the memory means in my data structure, we have different nodes values, that particular nodes A star value, heuristic value, all those things we have to store. But here in the local search algorithm, we have to store only one value, one node, which is the current node. Current node means if we have started from the initial node, then initial node will be my current node. And from the initial node, let's say I have chosen another its children, so that children will become the current node. So a node which is about to explore is called current node, and that generally move only to neighbor of that particular node. So definitely current node, from the current node, where will go to its neighbor, right? So here we doesn't have much information. We have the current node and its neighbor information. That's all. Typically, the path followed by the search are not retained, means the path is not going to store anywhere. Although local search algorithm is not systematic, they have two key advantages. This particular local search algorithm is not a systematic algorithm, but we have some advantages. What are the advantages? The first advantage is we use very little memory here, usually a constant amount. We have some memory, and that memory is constant, maybe 1 or 2, but it is very little. They can often find reasonable solution in large or infinite state space for which systematic algorithms are unsuitable. What it is saying, if the state space is very large, if the state space is very large to store into the memory, for those type of problems, this local search algorithm will give you good solution and very quick solution. Why? Because we doesn't have to store much node here, right? In addition to find goals, local search algorithms are useful for solving pure optimization problem, in which the aim is to find the best state according to an objective function. Now here we'll choose the optimal, we'll try to solve the optimization problem in the local search algorithm. And how we'll find out the optimum result? based on the objective function. Objective function is any type of constraint by which we choose which particular node will be the optimum node or the optimum goal. So if we have some alternative goals or alternative solutions, so from that we can find it out like which one will be the best one. So we will get it with the help of objective function. We'll learn about this objective function into later on algorithms. Many optimization problems do not fit the standard search model introduced in the previous topic. So in the previous topic, the optimization problem was not matching with that, but later on when we'll see some of the searches, so definitely we'll talk about optimization. So we have two things. One is the local search, and local search may lead us to solve some optimization problem. Okay, let's talk about local search again further. Now this is an example. Let's say you have an objective function. That objective function is either you have to reduce the cost, right? So the objective of anything is to reduce the cost. Okay, and this one is telling you about a state space. If the state space is very high and the objective function we have to achieve, some objective function we have to achieve, so this is actually telling you that how much the objective function you can reach with the state space. If the state space is more, how much you can reach. If the state space is less, how much you can achieve. Now this particular graph will telling you based on the local search. What is the meaning of local search? Local search means if some solution, if we are here in this particular point, if we are if we'll see, if we are here in this particular point, what is the value that we're getting is the up value, right? So do we get the up value? Yes, we are getting the up value. So we are getting the up value. Slowly we are increasing our chance to get the optimal solution. We are reaching here, and after that we find out some flat value. Okay, so we are saying that we are not going towards the optimal solution. So either we'll stop here or we can go further to get our global maxima. So the global maxima is actually your optimal solution. So could we reach the optimal solution and or we reach the local maxima or the least solution? That is actually we are going to learn in local search algorithms and optimization problems. If you didn't understand, nothing to worry. I'll explain it again and again. Let's understand what this particular portion is saying. To understand local search, we find it useful to consider a state space landscape. So that is the state space landscape. State space, we know that like in a tree, if our tree is more, means if we have the initial node and we are going into the depth, we are getting a huge state space. If the state space has been increased, definitely those nodes we have to store somewhere, right? If we are not storing those nodes and we are going to the current node as the local search says, so state space is not a worry for local search algorithm, because we doesn't have to store all the nodes which are there in the huge state space. Instead, we'll choose one, and that one will be my next, and then again one. In that way, I'll go. So in the local search algorithm, it is saying that you can see only your neighbor node. You cannot go further. It means you doesn't have the information of your previous ancestors, and you doesn't have the information of your siblings. What information you have? Only your neighbor node, which is going to forward direction. A landscape has both location. So here we have different locations defined by the state, and elevation. Elevation means this is the elevation. This is again elevation. Okay, this is again elevation. Elevation means how we are going up into the direction. Defined by the value of heuristic cost function of the objective function. So objective function or heuristic function will giving you the cost. That cost is nothing but your elevation. If elevation correspond to cost, then the aim is to find the lowest value. Lowest value, the global maxima. This is our objective, to find out the global maxima, where we have the greatest objective function. We achieve the greatest objective function. If the objective function is to find out the least cost, so this is my least cost for that, to getting the greatest objective function. If our objective is to get the highest cost, so this is my value where we are getting the maximum objective function. So objective function will be getting the maxima or getting the minima. It is based on your problem, whether we are getting the maximum value of the objective function or we are getting the minimum value of the objective function. In both the cases, it is called global maxima. Okay. If elevation correspond to an objective function, then the aim is to find the highest peak, a global maxima. You can convert from one to the other just by inserting a minus sign, so you doesn't have to worry about it. Local search algorithm explore this landscape. A complete local search algorithm always find a goal with one exist. So what it is saying that, it is saying that local search algorithm, a complete local search algorithm always find the goal. So we have local search algorithm which find or may not find the goal, but the complete local search algorithm always find the goal. If a local search algorithm is a complete, we say it finds the goal. An optimal algorithm always find the global maxima or global minima. If this is about local search always find the goal. It is no doubt about it. But the optimal algorithm always find the global value, the global maxima or global minima, whatever is required. If the objective function is to find out the minimum value, we'll get the global minima. If the objective function is to find out the minimum value, so we'll get the global minima. That is the objective. If you'll see here, there are different state of it. This is called solder. This is called flat local maxima. This is called local maxima. So local maxima means if I am in the current state, this is my current state. So if I'll reaching that particular peak, actually that peak look like the solution, but it is not the solution. The solution is this. That's why this peak is called local maxima. And this particular part is called flat, is again the part of local maxima. Okay. We'll see it further. What is that? With the help of one example. It's called hill climbing search algorithm. That hill climbing search algorithm is an example of local search algorithm. What happened in the local search algorithm? Let's say we are climbing into the hill. Okay, we have a hill. Let's say this is the hill, and we are climbing into the hill. So you see, this is how a hill look like. And what is my constraint? My constraint is I can only see, let's say, my next let's say 5 meter or 10 meter. Beyond that, I cannot see. So it is just like you assume that you are in the hill of the Everest, and it's very cold, and fog is there, right? And this cold cold wind is going on. So you cannot see beyond. So once you are going up, you are thinking that I am climbing the hill. Once you are going upward direction. So you are thinking that upward means, let's say you have started from here, you have started from here and you are going what, upward direction. So here you are, now you are going up in this way. So you are thinking that I am going up, and when you reach the hill and when you find the flat surface, you are assuming that this particular point is my goal, because you cannot see further. Getting it? This is the constraint in the hill climbing. Hill climbing says that you cannot see further. Instead, you can see your neighbor node only. So here, what is my neighbor? Neighbor is this particular points. These are the point are the neighbors. These are the point are the neighbors. And we find out that I am going to the flat. Means I reach the goal. But what is the goal? Goal is this. Actual goal is this. So what is my objective? My objective is to reach the global maxima. And this particular is called local maxima. Okay. So this is how hill climbing works. Hill climbing works if we are getting the greater value, greater objective function, I'll change my state from here to here, from here to here, from here to here, based on the objective function. If I am getting good values, once I am not getting the good values or I am getting the same value, so I'll not change the state. Instead, I'll be here and I'll assume that this is my goal. But this is not the goal. This is what? This is what? This is called local maxima. This is not the global maxima. This point is the local maxima. So let's go into this particular algorithm. It is a simply a loop. So this is the algorithm where we have a simple loop, a hill climbing. We have a problem. We are returning the local maxima. Here, because in the hill climbing, we are not getting the global maxima. Make node. What we are doing, the problem initial state. So whatever the initial state is, we are making that state as the current state. Now we are in the loop. A highest value successor of the current node. So we have the current node, and whatever the successor is, whatever the children is, if they are having the highest value or the highest value than the current node, those nodes are my neighbor node. If neighbor node value is less than the current value, means whatever my value is, if it is less than or equal to the current value, so I am in the current value. I'm not going to change it. Otherwise, that neighbor which has the higher value than me will become the current state. Getting it? Let's say if you are assuming that this is my initial value, and when I am going further, I find this particular as my neighbor node. This node is a neighbor node which has the higher value than me, higher objective function than me, definitely. So this particular value or this particular neighbor will become the current state. And from the current state, again, I'll go to the neighbor of it. This particular neighbor is again higher value. So I'll choose this node as the current node. In that way, I'll move on. When I'll reach here, so what is my neighbor? Neighbor is this. So this neighbor value and this peak value, the value will be the same. So I'm not going to change. Instead, I'll be in that particular current state. So that thing, I'll do it for one time and I'll go out of the loop because I am returning the current value. So I'm going out of the loop. And that is that particular value is my goal node or the goal value. But this is actually local maxima. This is not the global maxima. That is the problem related to hill climbing. So we have to go up uphill we have to do, and we have to stop once we are not going up. That's all. It terminates when it reaches the peak where no neighbor has the higher value. This is the algorithm. The algorithm does not maintain a search tree. So because it is a local search algorithm, so we are not making the search tree. We are not going to store the search tree. We have only one information, that is current node, and we have another information, that is what is my neighbor node. That's all. So the data structure for the current node need only record the state and the value of the objective function. So objective function value should be there associated with each and every node, and there should be the current node and its neighbor node. Hill climbing does not look ahead beyond the immediate neighbor of the current node. I was saying that in the hill climbing, we just see our neighbor. Beyond that, we cannot see. This resembles trying to find the top of Mount Everest in a thick fog while surfing from amnesia. It is saying that it is just like you are in the Mount Everest with a thick fog, and you cannot see the more further routes. The hill climbing search algorithm, which is the most basic local search technique, at each step, the current node is replaced by the best neighbor. In this version, that means the neighbor with the highest value, but if a heuristic cost estimate h is used, we would find neighbor with the lowest h value if we the objective is to find out least h. So that hill climbing algorithm, first of all, it is a local search, so it can see only its neighbor, not beyond that. Second, it is using the greedy approach, means who is having the least cost or good objective function, I'll go there. And there is no backtracking. I cannot go back. So that is how your hill climbing works. So let's take one example, how we can give an example here. Let's take one example. Let's say we are having one node, and this node is having, let's say, 3 children node. Okay, so we have, let's say, 1, 2, and 3 children. Let's say the objective function, or you can say the heuristic value here, it is, let's say, 7. Okay, and the heuristic value here, it is 3. Here it is, let's say, 5. Here it is, let's say, 6. Okay, now I am in the current state. These are my neighbors. So where I have to go, could you tell me here? So here 7, because which is the best one here, I can find it out. What is the best one here? I can find it out is 3, 5, or 6, right? So I can choose 3 as the best one, right? Because it is having the least cost. So instead of going this and this node, I'll just leave this node. I'll not go there. I'll not store anywhere. So these 2 nodes will not going to store anywhere. Instead, this current node will be replaced by this node. So now this node will become the current node, and this node will also remove from the memory. Now this is my current node. Which one? Which is having the value 3. Now 3 has maybe 2 neighbor. So this is one neighbor and this is another neighbor. Now this value is, let's say this is 1, and this value is, let's say, 4. So which one I'll go? I'll go to this direction because it is having the least heuristic value. So I'll just remove this from the memory. I'll just remove this from the memory. Now I have only this current value. If I'm going further, let's say we'll get the value, let's say this value and this value, and both the value has value, let's say 1, and this value is 2. So which is having the least value? So you cannot find any least value. So what you do is, you will not go here, neither you will go here. You will be in this particular state only. So this will become your current state, and this will be removed from the memory again. These two will be removed from the memory again. And what is your the local maximum that you will get is this way. This is your local maximum, right? This is how it works. This is how it works. So I think you understood the hill climbing algorithm. Now we'll go to the drawback of this particular hill climbing algorithm. Let's talk about this. We have some problems. One problem that you have understood is local maxima. Why it is a problem? Because of the local search, we cannot go to the global maxima. Now, if we are starting our process from here, if you see this example, if we are starting our process from here, we are reaching this goal. And after that, whatever the value is, it is less than that. So we are not going to change my current value. And this value I am taking as my solution for the problem in the hill climbing algorithm. And this particular is local maxima. And this particular is global maxima. Actual value is global maxima. But what I find local maxima. That's why it is a problem. The local maxima is a peak that is higher than each of its neighboring state, but lower than the global maxima. Hill climbing algorithm that reach the vicinity of the local maxima will be drawn upward towards the peak, but will then be stuck with nowhere else to go, because the algorithm says that you cannot if we have least value, you cannot change your state. If you're not changing the state, how you'll go further, right? So hill climbing algorithm will not give you the optimal solution. That's all. Hill climbing algorithm cannot give you the optimal solution. Will give you the solution which is not optimal. That's all. Second problem is plateau. What is plateau? Plateau is a flat area of the state space landscape. It can be flat local maxima from which no uphill exists, or a shoulder for which progress is possible. Now, if you see this particular surface, so this particular surface is a flat surface here. This particular surface is a flat surface here. So if you are reaching this particular state here, we cannot go further. Why we cannot go further? Because all these values are equal to this value. That's why this is another problem. If you are getting the flat surface, so you cannot go further. Instead, you will be here and you are choosing this as your goal. But this is not the goal. This is local maxima. Locally, it is maxima, but it is not globally maxima. Okay. If you are getting a ridge surface, ridge result in a sequence of local maxima, which is very difficult for greedy algorithm to navigate. If you see, this is a 3D diagram where we have X, Y, and Z surface. You see, you have started your journey from this particular ramp. So you are going to up into the hill, and you are reaching that particular state. Once you are reaching the state, the further is the flat one. So you cannot go here, right? But in the same level, there is a point B. Definitely the value here is more than this value because it is going upward. See, but the hill climbing algorithm cannot change the direction. It cannot change the direction. So it will not go here. Instead, it will be here and say this particular point is the global maximum. This particular point as a solution. But this is actually the local maxima. This is a local maxima. This is not the global maxima. Where you have the global maxima is point B. Point B is your global maximum here, but we cannot go there. Okay, this is ridge. So we have three type of state space. You can see this state space will tell you the value, how the value is increased, how the value is decreased, and how the value is going into flat way, right? So this is all about hill climbing algorithm.